Transistors, before being put into service, require biasing. Biasing is an act in which DC voltage sources are connected, usually with the help of a resistive network. After biasing, the transistor's emitter junction, it goes into forward bias, and collector junction goes into reverse bias. If we want amplification or amplifier configuration out of the transistor, after biasing, certain currents, terminal currents get established in the circuit. Certain voltages, junction voltages, they come into being in the circuit. The terminal currents and junction voltages, they are related to each other. Currents are also related to each other. The interrelation between currents and voltages after biasing, this information is quite useful for us, as it helps us in designing an efficient bias circuit, an efficient amplifier circuit, a stable amplifying circuit. This information is provided, available in the form of graphs. Two graphs for each configuration. One graph represents input characteristics, another graph represents output characteristics. As there are three configurations, in total we have 6 sketches or graphs. Input characteristics denote the relation between input current and output current for different output voltages, and output characteristic denotes the relation between output current and output voltage for different input currents. There is a model, it is called Ebers-Moll model. This is also a highly efficient method by which DC characteristics of transistors, BJTs, are expressed. Electronic devices, BJTs static characteristics, series on semiconductor devices and circuits, lecture number 3.10. Ebers-Moll model describes the behavior of BJT under static conditions or DC conditions. When the transistor is in active mode of operation. Apart from Ebers-Moll model, in the present session, we focus on configurations, BJT configurations, and transistors behavior when it is in one or other of these three configurations. BJT can be placed in CB configuration, in CE configuration, or in CC configuration. Their static characteristics, they are studied under two heads: input characteristics, output characteristics. Now we move further to study the static characteristics of BJTs in different configurations. Let us start the session by considering the convention. This convention pertains to currents and voltages that are there in a transistor circuit. The currents IE, IB, IC, these are positive when entering into transistor and negative while leaving. This is standard convention. I means current, E means emitter, again B means base, I means current. Here also I is current, C is collector. So here the subscript refers to the terminal. These are considered positive while entering and negative while leaving. The voltage VEB is interpreted as voltage of emitter with respect to base. V stands for voltage. Voltage of emitter with respect to base is emitter's voltage. Reference is base. So second subscript refers to reference. As all are capital letters, it is pure DC. All capital means DC. Similar is the case with the other voltages. Some more information regarding convention can be understood by considering base current. Capital I, capital B, it is base current. As both are capital, it refers to pure DC, DC base current. Next is small I, small b. B is subscript small b. I is current, B refers to terminal as already told. So as both are small letters, this current refers to AC, AC base current. Now we move further, small I, capital B. Capital B is the subscript. This current refers to DC plus AC base current. Notice when a transistor is functioning, there exists two types of currents at any point in the circuit. Certain DC current, it is as a result of bias voltage. Certain AC current, AC component, which is a result of signal source connection, and these two together exist there at any point. So total current is the sum of DC plus AC. DC part is denoted by capital I, subscript also capital. AC part is denoted by small I, subscript also small. Total current is denoted by small I, capital subscript. Sometimes we also come across capital I, small b. It refers to RMS value or DC value of base current. RMS. It is pure AC, therefore 0, so RMS value of base current. Some points regarding Ebers-Moll model. In 1954, J.J. Ebers and J.L. Moll presented a compact formulation for current voltage characteristics of BJTs based on coupled diode model. One point to be noted while going further is that equivalent circuits can be divided into several categories. For example, small frequency, high frequency, small amplitude, large amplitude, small voltage, large voltage, etc. Similar such a division is DC equivalent circuit and AC equivalent circuit. DC model, AC model. We consider AC models later. Now we are into a DC model, a popular model. It is called Ebers-Moll model. It describes BJTs, DC characteristics in a circuit form. In this model, the emitter and collector junctions are treated as two diodes connected back to back along with the two current sources which are controlled by diode currents flowing through opposite branches. Coupled diode model. Diodes are used profusely in this model. Two junctions are there in BJT. Each junction is replaced by one diode. Here is shown the actual model: emitter, base, collector. IC is collector current, IE is emitter current, IB is base current. In this model, one can see two diodes. Each diode is in parallel with one current source, alpha IIC, alpha IIC. Here also alpha IIC. In the first part, minus IEO. In the second part, minus ICO. A few points regarding this model. These points help us in understanding this model. This model involves two ideal diodes placed back to back with reverse saturation currents, minus IEO and minus ICO or IE naught, IC naught. And two dependent current controlled current sources shunting the ideal diodes. For PNP transistor, both IEO and ICO are negative, so that minus IEO minus IC naught are positive values. This model is valid for both forward and reverse static voltages applied across transistor junctions. It means last point implies that this model is valid for all the three regions of operation. Some more points regarding Ebersmall model. The interdependence of currents and junction voltages in a transistor can be expressed as IC equal to minus alpha n IE minus IC naught e power VC by VT minus 1. Notice this part is diode's equation, Shockley diode's equation. So diodes are there in the model, therefore naturally in the analytical expression, diode's current automatically comes into being. The subscript N here is added to indicate the transistor is being used in a normal manner. It is also possible to use the same transistor in inverted manner with the emitter and collector roles interchanged. In that case, IE is equal to minus alpha IIC minus IE naught e power VE by VT minus 1. The parameters alpha n, alpha I, IC naught, IEO are not independent, and their interrelationship can be expressed as alpha I, IC naught equal to alpha n, IEO or IE naught. Alpha I means inverse operation, alpha n means normal operation. Now, few points regarding configurations, BJT configurations. BJT is a three-terminal device. For inputting, two terminals are required. For taking output, another two terminals are required. But as there are only three terminals, one terminal must be common for input and output. If base is common, then that particular configuration is called common base configuration. When emitter is common, then it is called common emitter configuration. When collector is common, it is called common collector configuration. Here are shown CB configuration in A, CA configuration in B, CC configuration in C. In A, first one is PNP transistor, second one is NPN. In B also, first one is PNP, second one is NPN. In C also, first one is PNP, second one is NP. Notice in all these cases, in A, in B, and in C2, the transistor is in active mode of operation. Emitter junction is under forward biased condition. Collector junction is under reverse biased condition. Here are given comparison of configurations. In second column, current gain, voltage gain, Ri, R0. Ri means input resistance, R0 is output resistance. In the third column, these quantities are given for CE. Current gain is high for CE, voltage gain also high, minus 46.5 is current gain, minus 131 is voltage gain. For CE, input resistance is 1 kilo ohm for CE, output resistance is 46.5 K. This is for C. For CC, current gain is high, 47.5. Voltage gain is low, nearly 1, but less than 1. RI is high, 144 K. R0 is low, 80.5 ohms. In case of CB, current gain is low, 0.98. Voltage gain is high, 131. Input resistance is 22.5 ohms. R0 is high, 1.72 mega ohms. One point before going further to know is, in case of CE, notice minus sign is there against gains, which is absent in case of CC and CB. This negative sign, minus sign, indicates that output voltage is out of phase with input voltage, or output current is out of phase with the input current. So currents, output current and voltages are out of phase with the input current and voltage. Now CB configuration. Here is shown CB configuration, PNP transistor, NPN transistor. So point to be noted here is base is common. So this is CB configuration. Input side current and voltages are IE, VEB. So this is IE, VEB. Output side current and voltages are IC. This is IC, this is VCB. Yeah. Similarly, if we come to NPN transistor, this is VEB. This is IE, this is IC, this is VCB. Here are shown input characteristics of PNP transistor. CB configuration transistor. Horizontal axis represents emitter current, vertical axis represents emitter to base voltage. One can see several curves in this graph. Each curve for a particular value of collector to base voltage. Top one is when collector base is open. Next one is collector to base voltage is 0. Next one is when it is -1. Next it is -10. Next it is -20. One can notice the similarity between these curves and forward biased junction diode characteristic. Salient features of these input characteristics. The input characteristics represent simply the forward characteristic of emitter to base diode for various collector voltages. The input characteristics exhibit a cut-in voltage V gamma approximately equal to 0.1 volts for germanium, 0.5 volts for silicon transistors. The curve with the collector open represents simply the characteristic of a forward biased emitter based diode. Shape of input characteristics can be understood easily by considering increase in emitter current with increase in magnitude of collector voltage due to early effect. So point is to understand these curves. Two things are essential or required. One is forward biased diode characteristic. Second one is early effect. These two together gives us complete information, total information, clear information regarding the input characteristics. The combined effect of increase of emitter current with the collector voltage as well as with VEB leads to shifting of curves downward. Now output characteristics of CB configuration. Horizontal axis represents VCB, vertical axis IC, collector current. Some points one can notice very easily. Several curves are there. Each curve is for one particular value of emitter current. Top curve is for emitter current of 40 milliamperes. Second one is next to second one is for 30 milliampere. Then we have a curve for 20 milliamperes, like that 10 0 also. So this particular graph is VCB versus IC for different values of IE, emitter current. This is one point. Another point is, notice this particular curve represents IE equal to 40 milliamperes, and it is at an IC of 40 milliampere. So IE and IC, they are almost equal. Similarly, 30, 30. IE is 30, IC is also 30, of course, negative sign. 20, 20, 10, 10. And this is the case, notice, when the diode is in active region. This one, active region is indicated here. When transistor is not in this region, of course, IE differs from IC. For example, if you consider this curve represents IE 40 milliamperes, but here IC is around 28 or so. They are not equal. So in active region of operation, transistors collector current and emitter currents are almost same. So this is second aspect. Third aspect is total operational region is divided into three parts. Active region, left side you can find saturation region. At the bottom we have cutoff region. Active region means emitter junction under forward bias, collector junction under reverse bias. Saturation means both junctions under forward bias. Cutoff region means both junctions under reverse bias. A few points regarding output characteristics of CB configuration. It is customary to plot VCB along horizontal axis, abscissa. To the right, that polarity of VCB, which reverse biases the collector junction, even if this polarity is negative. The total graph can be divided into three regions representing active, saturation, and cutoff. A few points regarding active region. Here, the collector current is independent of collector voltage and depends only upon emitter current. As a consequence, the curves are horizontal straight lines in active region. However, because of early effect, notice everywhere this effect, early effect, comes into picture. There actually exists a small increase in IC with VCB, and the magnitude of collector current is slightly less than that of emitter current. Saturation region. The region to the left of the ordinate VCB equal to 0 and above IE equal to 0 curve in which both emitter and collector junctions are forward biased is called saturation region. This region is characterized by bottoming. The curves have fallen to the bottom of the graph where VCB is nearly 0. A few points regarding cutoff region. The region below IE equal to 0 curve for which emitter and collector junctions both are reverse biased is cutoff region. Note that IC is 0 curve is not coincident with voltage axis through the separation is difficult, though the separation though the separation is difficult to show because ICY is only few nano amperes or microamperes. Now we consider CA configuration. Important point to note is in these diagrams, emitter is common for input and output. That's why it is CA. Input side current and voltages are base current, base to emitter voltage. Output side current and voltages are collector current and collector to emitter voltage collector. So input characteristics and output characteristics we see. Here is shown typical input characteristics. Base current, base voltage for different values of collector to emitter. This is also similar to forward biased diode characteristics. Exponential rise in current with voltage. Not much is available to discuss further. These are output characteristics. Horizontal axis represents collector to emitter voltage VCA. Vertical axis represents collector current. Several curves can be found. Each curve pertains to certain base current. Notice Collector current is in tens of milliamperes, whereas base current is very small, not even 1 milliampere. Usually, emitter current, most of the emitter current, it appears at the collector terminals. So emitter current and collector current, they are almost same. Base current is very little, very small. Here also one can find active region. Active region is this part. This is active. Whereas the left side it is saturation region, bottom it is cutoff. Now we consider CC configuration. So here collector is common. Collector is common. Notice the commonality should be determined from the point of view of AC, signal source, not DC. When you ignore bias sources, only signal source exists in the circuit, then the common terminal becomes visible. The commonality factor becomes more clear. Anyway, CC configuration means collector is common. Input side current and voltages are IB and VI. Here is VI, here is IB. IB, VI. Output side current and voltages are IE, V0. Here is IE, V0 is, this one is V0. Input characteristics of a PNP transistor in CC configuration are shown. Horizontal axis represents base current, vertical axis base to collector voltage. Notice with increase in base voltage, base to collector voltage, base current is falling. No, base current is falling. And two curves are shown, one for VAC minus 2 volts, another VAC minus 4 volts. A few points regarding input characteristics of CC configuration. The input characteristics of CC differs quite well with those of CE or CB. The variation is mainly due to dependence of input voltage VBC on output voltage VAC. Base current IB in active mode of operation is nearly equal to emitter current IE, which on the other hand depends only on forward voltage across the emitter junction, VEB. It appears then that IB is independent of base to collector voltage VBC, but it can be observed with increase in VBC, voltage across the emitter junction decreases, increasing the level of VBC with VEC held constant, reducing the base current to emitter voltage VEB, thereby reducing base current IB. And this reason for which the CC input characteristics exhibit slope. Here is the shown output characteristics of CC configuration. Emitter voltage, emitter current for different base currents. One point one can note, common point, simple point, ordinary point is base current here is 50 microamperes, whereas corresponding emitter current is 7 milliamperes. Base current is small when compared to emitter current or collector current. It is always small. Whatever may be the configuration, whatever may be the transistor type. A few points regarding output characteristics of CC configuration. It is a graph representing emitter voltage VEC versus emitter current IE for different values of base current IB. For a BJT, the emitter to collector currents are nearly same. It is true emitter and collector currents remaining same is true for all the three configurations. Of course, when the transistor is in active mode of operation. Also, VEC is equal to minus VCE, and hence curve between VEC and IE is similar to that between VCE and IC, output characteristic of CE configuration. With this, we come to an end to this session. In this session, the focus is on convention that is followed regarding denoting the currents and voltages in transistor circuits, Eber's model, and input and output characteristics of different configurations. Hope this session is useful to you. We meet again in another session with a new topic soon.